We're going to continue with matrices and matrix algebra, and in this video we are going to talk about some properties of matrices in terms of addition and matrix multiplication. Right. So we start off with the theorem, and this is theorem 2.2.14, and it says suppose A, B, and C are m by n matrices, then the following statements are true. So remember that in vectors we had commutativity of addition, so we are going to also explore these properties and compare them with what we already know of real numbers mainly, and see which ones will hold for matrices and which ones will not hold for matrices. So the first one is commutativity of addition. So A plus B is equal to B plus A when we are working with matrices, and then associativity, the matrices associative under addition. So A plus B plus C is equal to A plus B plus C. So it doesn't matter which order you add matrices, that's what it's really saying. It's going to, you're going to get the same answer. And then the existence of an additive identity, we defined the zero matrix in the last video, in the previous video, and this turns out that A plus the zero matrix will be equal to A. And the existence of an additive inverse, so if we add A plus its minus, then you're going to get the zero matrix, or the additive identity, right? And so we are going to do a proof of one, and the rest is left as an exercise. So you'll do that as part of your work. So according to definition of addition of matrices, A plus B will be equal to the matrix Aij plus Bij, because we'll be adding the corresponding entries of A and B, right? And same applies with B plus A, it will be the same. But remember that these entries Aij and Bij are real numbers, so we know that if we add Aij plus Bij, it is the same as Bij plus Aij, because these are real numbers, right? So because real numbers are the addition of real numbers is commutative, so it means these two values will be equal. And if these are equal, it means that the sets themselves, sorry, not the sets, the matrices themselves, so A plus B and B plus A, are also equal. And this is from the definition of equality of matrices, definition 2.2.3. right, let's get on to the next set of results. So suppose A and B are m by n matrices, and R and S are real numbers. So then the following statements are true. So we've got some distributive laws. So we can distribute scalar multiplication over matrix addition, and that's what the first one is saying, that if you can distribute the scalar multiplication over the addition, so R of A plus B is equal to R of A plus R of B. And the second distributive law talks about scalar addition over matrix multiplication. So R plus S times A is equal to RA plus SA. And the third one is associativity of scalar multiplication. So we have RS times A is equal to R times SA. So we will be able to use these properties to navigate when we are doing addition, multiplication, whatever we are doing with matrices. And if you have got the multiplicative inverse of real numbers 1, then 1a will be equal to a. And if you also have the additive inverse of real numbers, that's 0. So if you say 0 times a, you will get the additive inverse of matrices. And if you do a scalar multiplication of the additive inverse of matrices, so R times the additive inverse of matrices, you still get the additive inverse of matrices, which is O, right? So we are going to do the proof of 3, and then the rest are left as an exercise. So what do we have? What do we know? So we have got definition 2.2.9, and this tells us about scalar multiplication, right? And it says that if you have RS times A, you can then say so you are multiplying the RS to every entry of A, so you end up with something like that. And if you multiply R by SA, it means that the entries of SA were originally SAIJ, and then you multiply by R, so that's why the bracket is there, right? But the multiplication of real numbers is associative. So in other words, and remember that all these three inside there are real numbers, so we know that the set of real numbers is associative under multiplication. So that means RS times AIJ is equal to RS times R times SAIJ, and the bracket is supposed to be there, right, for every entry of the matrix. So that's what we mean by for every I and for every j, right? So because these are equal, it means that whatever is in there is equal to there, and therefore the corresponding matrices RS times A will be equal to R times SA, and that is because of the definition of equality of matrices, definition 2.2.3. Right, so you can do the rest as an exercise. Right, let's get on to more distributive laws, and now we are talking of matrix multiplication. Now suppose A, B, C, I and O. So the I and O, we are talking of the multiplicative inverse for I, and then the additive inverse O for matrices, and all have suitable sizes so that the relevant operations are defined, and let R be a real number. And here by suitable sizes we are saying if you are multiplying A and B, so if you say AB, what we are saying is in that case we are expecting the number of columns of A to be equal to the number of rows of B, sorry, and that will then guarantee that the operation AB will be defined in that case. Otherwise it will not be defined if that is not if that doesn't happen. So that's what is that's what it means to say suitable sizes, right? Then the following statements are true. So associativity of multiplication. So multiplication, matrix multiplication is associative under multiplication. So in other words, ABC, AB times C is equal to A times BC, right? So again, it doesn't really matter which order you take. It means we are going to get the same answer. And then the first distributive law, and we are distributing matrix multiplication over matrix addition. So A times B plus C is equal to AB plus AC. And then the second distributive law is now we are doing it on the other side. Remember, well, we talk about the fact that matrix multiplication is not commutative, so we really need to follow the order that the matrix is being multiplied. So here, that's why we have got a distributive law for left-hand multiplication, and now for right-hand multiplication, right? So now we are distributing right-hand multiplication over matrix addition, and we get that. And then we also have the existence of a multiplicative identity. So in other words, IA is equal to A. When we defined it, we said it is the identity, and now we are seeing that the property for identity actually holds, that IA is equal to IA is equal to A, and AI is equal to A, right? And then again, if we take the multiplicative the additive inverse of matrices O, and you multiply it with A, you get O. And then again, if you do it on the other side, so in 5 O was on the left, and then in 6 O is on the right. So we are going to do a proof of 5. Okay, so there's an error here. It's supposed to be 3, 4, 5, 6, 7. So we'll correct that in the slides that will be posted on ClickUp. Right, so what the proof that we want to do is this one. That is the original 5. If I am, yes, I think I'm right. Maybe this one. Anyway, one of these. Right, so let I be the m by m identity matrix, right? And A be the m by n, be an m by n matrix, right? So, and let D be Dij, which is equal to Ia. So what we want to show is the entries of A are the same as the entries of D, right? And then we would have shown that Ia is equal to A, right? So for each I and J, so in other words, for each entry, Dij is equal to OI1 times A1J plus I2, sorry, here it's supposed to be I2, is A2J up until, so, and then we have this special entry because we know that when we are talking of identity of the identity matrix, this OII is special because that's when the entry becomes 1, but the rest will be zeros, right? And up until OIM times AMJ, right? So for OII, sorry, for OIJ, we know that OIJ is equal to 0 if I is not equal to J, and OII is equal to 1, right? And this is for OI and for all J, right? So the diagonal entries are the only ones, in other words, so the J here is cut, but otherwise it's saying OIJ is equal to 0 when I is not equal to J, and then all the diagonal entries are 1s. So what it means is when we add here, all these entries are zeros. So you are saying 0 times a1j plus 0 times a2 a2j plus up until that, and then when we get here we get OII, which is equal to 1. So in other words, this entry becomes 1 times aij, which is equal to ij, and then the rest of them become zeros. So what it means is all these entries, so in other words, dij in the end becomes equal to 1 times aij, because the rest of them are zeros. So that means dij is equal to aij for all I and for all j, and because of that, that means that the two matrices D and A are actually equal by the definition of equality of matrices. Right, so that is that. The rest of the results here you can do them as exercises. Right, so a remark, that's remark 2.2.17, and it says that if you have a matrix, a square matrix A, then A squared simply means A times A, and then you can write A cubed to mean A. So we do have, so when we have a square matrix, we can talk of powers of matrices, right? The same way as if you've got a number 2, you can say 2 squared, 2 cubed, 2 to the n. So if you have a square matrix, so it only happens when you do have a square matrix, then you can talk of powers of A, and that's how you find the powers of A. Right. Now, so we talked about properties that do hold for matrices in Theorem 2.2.15 and Theorem 2.2.16. Now we want to talk about things that properties of real numbers that we will not find in matrices. So for example, the first property that we're going to talk about is matrix multiplication. So matrix multiplication is not commutative, whereas in real numbers we know that in real numbers AB is equal to BA for every AB, but in matrices this is not true in general. And we have got an example. So if you do, suppose A is equal to suppose A is equal to 1 0 2 minus 1, and B is equal to 1 1 2 3, then if you calculate AB and you calculate BA, so again, as I mentioned before, the order of multiplication here matters, simply because AB is not equal to BA, and we can see it in these two products, that AB is not equal to BA, right? So you can just verify if that is true, if the entries are correct here, but otherwise AB will not be equal to BA, right? Now we go on to the next property. So what we know about real numbers is that if you do a product of two real numbers and you get a 0, then it means that at least one of them, of the numbers that you multiplied, is equal to it should be equal to 0, right? And what that means is, that property is that there are no 0 divisors in R, right? And so for matrix multiplication, this is not the case again. So if you take, for example, the matrices that we are given, A is equal to that and B is equal to that, you'll see that we can see that A is not the 0 matrix, B is not the 0 matrix, but if you do the multiplication AB, you'll find out that you'll get the 0 matrix, meaning that we multiplied two non-zero matrices and we got a 0 matrix, which does not happen in real numbers. So for matrices, there are 0 divisors. In in real numbers there are no zero divisors, but whereas in matrices there are zero divisors, as this example shows. Now let's go on to the next property that we find in real numbers, and that is the cancellation law. And the cancellation law says that if you have three matrices, if you have three real numbers, so that AC is equal to BC and C is not equal to 0, right? Then A is equal to B. And in real numbers, what you just do there is you divide by C, and then you get A is equal to B, right? But in matrix multiplication, this is not true, simply because, so here the idea on real numbers is the fact that if C is not equal to 0, then C has a multiplicative inverse. Whereas in matrices, a matrix might not be equal to the 0 matrix, but it might also not have a multiplicative inverse. So in this case, that's why C, if you look at C, you see that we haven't talked about inverses of matrices, but you can see that in this case the determinant is 0, so therefore, yeah, we'll talk about that later, but the determinant is 0, and so therefore the C here does not have an inverse. So that is why the property holds in real numbers, because every number that is not 0 has an inverse, whereas in matrices that is not always true, that if it's not the 0 matrix, it has an inverse. So you'll see that even though A is not equal to B, AC will be equal to BC in this case that we are talking about. So therefore the cancellation law does not hold for matrix multiplication, right? So we have talked about the issue of an inverse. So this is the example. So if a non-zero real number, if you have a non-zero real number, then it is going to have a multiplicative inverse. So what it means is there exists a real number A inverse, so that A times A inverse is equal to A inverse times A, which is equal to 1. For matrices, this is not true, and we pick an example of a matrix with that, which is a counterexample to the property. And suppose this is the 2 by 2 matrix, and then if we had an inverse, then it would mean that if I say A times that candidate AB, we should be able to get I. We should be able to get the identity matrix, right? But you'll see that if we try to do that, so it follows from the definitions of equality of matrices and matrix multiplication that if you do the multiplication of A and the Bij, so A, so you'll have B11, so Bij will be B11, B12, B21, B22, right? And then if you do AB, if you multiply A times the B, you find out that for this to be equal to I, we are going to have 1 is equal to D11, which is equal to B11, and then 0, which is equal to D21, should be equal to 3B1 when you do the multiplication. And this means that B11 in this case is 0, B11 in this case is 1, so 1 will be equal to B11, which is equal to 0. But we know that 1 is not equal to 0, so we get a contradiction. So if the inverse existed, then it would lead us to a contradiction. So therefore it means that this matrix B does not exist. This inverse that we thought would exist does not exist. Right. So those are some of the properties that matrices that do not hold, that are in real numbers, that can be that don't hold for matrices. So let's get on to another way of creating new matrices. So suppose you've got an m by n matrix, then what we call the transpose of A, and it's written A to the power t, so AT is the n by m matrix. So when you transpose, you get an n by m matrix. You started off with an m by n, you get an n by m, such that the rows and the columns are reversed, right? So what is the new bij is the old AJI, right? So let's illustrate that with an example, but maybe we can talk about the remark first. If A is an m by n matrix, then the ith row of A transpose is the ith column of A. So that's what it means here when we reverse the order of the rows and columns. It means that so let's look at an example to just clearly see what happens. So A will be equal, suppose you've got A, which is 2, 3, 4, 5, 6, 7. So what it means is when you transpose, so this was a 2 by 3, it becomes a 3 by 2, right? Is what is in the definition. And then you notice that the first column becomes the first row, the second column becomes the second row, and then the third column becomes the third row. Or if you want to talk of rows, the first row becomes the first column, and the second row becomes the second column, right? And you just see that we have flipped. So where we had so let's take the entry A13, right? So A13, 4. So this 4 becomes A31 in the transpose, right? And you can see that that is what happened there, right? So now we have new matrices. So we are going to talk about properties of these transposes of matrices, right? So okay, so another example. So if you have a column vector like that, you can make it a row vector by transposing. So this was a 3 by 1 matrix that becomes a 1 by 3 matrix, right? Right, some properties of transposes. So let A and B be matrices of suitable sizes. Then the following statements are true. So we are going to prove one of them, and then the rest are left as an exercise. So the transpose of the transpose is equal to A, right? So if you transpose a matrix 2 times, you end up with the original matrix that you had, right? And then the second one, the sum of the transpose is equal to the transpose of the sum, or so the transpose of the sum is equal to the sum of the transposes, right? So A plus B transpose is equal to A transpose plus B transpose. And then the last one is the transpose of the product is equal to the product of the transposes. So the transpose of AB becomes it becomes B transpose A transpose, right? but you need to note the fact that they will be in reverse order, right? So here we had AB, here we are starting with B, the last one, and then going to the first one, right? So that is very important. As you go on, you might see that if you don't follow this order, you definitely get different answers in different situations, right? So the proof of number 2. So assume A and B are m by n matrices. Then let C be the transpose of the sum of A and B, and D be the transpose of A plus the transpose of B. Now, what do we know? We know that Cij, which is the transpose of the sum, will be equal to Aji plus Bji, because we would have transposed the sum of A, right? So we would have said A plus B. We would have gotten Aij plus Bij. But if we transpose, then it means the entry will now become Aji plus Bji. But this is the entry of A transpose, and that is the entry of B transpose. So that becomes Dij, and by definition of equality of matrices, that means that these two matrices become equal. Right. So that is the proof, and then the rest you can will be left as an exercise. Now consider the system of linear equations. So we've got a11 x1 plus a12 x2 plus a13 x3 equals to b1, and then a21 x1 plus a22 x2 plus a23 x3 is equal to b2, and then a31 x1 plus a32 x2 plus a33 x3 is equal to b. And then let A, so there is no transpose here, that would need to be corrected. Let A be equal to a11, a12, a13. So we're just taking the coefficients of the left hand side of all these equations, and our x become the column vector, the 3 by 1 vector, x1, x2, x3, and then b to be that. Then what we know is if we take so if you look at a, forget about this, a and times x, you notice that ax will just be the matrix, so it's just taking literally this to be a matrix, but a matrix with 3 rows and 1 column. Remember, we are adding here, so it's just one, so it's 3 rows, so it's a 3 by 1 column, and obviously it's going to be equal to a 3 by 1 column. A 3 by 1 matrix will be equal to also to a 3 by 1 matrix. So if you think of this as a matrix, that is the AX that we have here, it is just a 3 by 1 matrix is equal to a 3 by 1 matrix. So if we can find values for x1, x2, and x3, which is a solution to 2.2 to this system, then it has to satisfy the fact that ax will be equal to the b, where b is where B is the, what do you call it, the entries, the terms on the right side of each equation, right? So if it is a solution, then it will have to satisfy that. Remember, x1, x2 are unknowns, so if we find x1, x2 and x3, which will be a solution to the system, then they have to satisfy this equation. So therefore, the system of linear equations 2.2, which is this, is equivalent to having this system. And as we go on, we'll see that when we are actually trying to solve for x, we don't really need to use the x in the system that we'll create. We'll only need the x's when we are done, when we are solving right at the last part. Okay, thank you.